right, so yeah, welcome everybody to today's Quasiworld seminar. So our first speaker is Malavika Mukundan from the University of Michigan, and she will tell us how to construct dynamical approximations for entire functions. So please, Mala.
Hi, everyone. Thank you to the organizers for having me here. So this talk is somewhere at the intersection of complex dynamics, topology, and a little bit of geometry. Okay, so I'll state the main results like right at the beginning, and then I'll start going into the theory. Okay, so this is joint work with Nikolai, Prochorov, and Bernhard, who are both students of Dec6th. They both Nikolai is based in Marseille, and Bernhard just moved to Leipzig.
So Mala, sorry to interrupt. Your audio is somehow suboptimal. It's a bit hard to hear you.
Oh, just a second. Is this okay?
Yeah, that sounds better. Yeah.
Okay. So I'll just speak like this.
It's much better. Yeah.
Yeah. Okay, so let's start with some really basic stuff. So what is an entire function? It's a holomorphic map from the plane to the plane. Some examples are z goes to e to the z, cosine z, or this last function where you're taking an integral over some exponential of a square type thing. So the last function is called an error function. We'll also define an asymptotic value to be a value A on the plane, such that there exists some arc gamma which goes to infinity, but the image of that arc goes to A as the t parameter goes to infinity. Okay. So some examples include 0 for e to the z. So for example, if you take an arc that goes along the negative real axis and take the time parameter to infinity, that arc under e to the z maps forward into the unit disk and it approaches 0 as t goes to infinity. Okay. You can also check that root pi over 2 and negative root pi over 2 are asymptotic values for the error function, and that z goes to cosine z does not have any asymptotic values. Okay. So just to get a sense of what asymptotic values can look like, Picard's theorem tells you that in any neighborhood of infinity, every point on the plane except at most one has infinitely many pre-images in that neighborhood of infinity. So what this tells you is that an entire function can omit at most one point on the plane. So asymptotic values, in other words, need not be omitted values. So for example, the error function is actually surjective, so all the asymptotic values have infinitely many pre-images. Okay, but on the other hand, if you look at e to the z, 0 is in fact an omitted value, and it is also asymptotic. So fix f entire. So this talk is going to be a special kind of entire function, which I'm going to define now. So any critical value or asymptotic value of an entire function is called a singular value. Okay. And I will denote the closure of this set of singular values as S sub f. Singular values are defined analogously for any branched cover on the plane. You don't need holomorphicity to define either a critical value or an asymptotic value. Do I need to define what a branched cover is, or should I just go on?
Please.
Okay, yeah. Okay, I'm going to define it just in case. So, okay, a branch cover in this case of R2 is basically you have a discrete set in the codomain such that if you remove that discrete set and its full preimage, that the map is a covering. Okay, so that's what I mean by a branch cover. So in general, if you have any branched cover without any holomorphicity, so for example, every entire function is a branch cover. But if you just remove the holomorphic property, you can still define singular values for branch covers. And the point is that the set S sub f can be finite or infinite. In all the examples we've seen so far, SF is finite. So we'll just make one more definition. Given a branch cover F on the plane, the post-singular set of F is defined as the forward orbit of S sub f with the closure taken on it. So you take S of f, S sub f, f of S sub f, f of S sub f, and so on. You take the union of all these and you take the closure of that. So that's the post-singular set. And f is said to be post-singularly finite, or PSF if this set is finite. Okay. So one example is 2 pi I e to the z. So let's see what the singular values are this function f of z does not have any critical values, and it has a single asymptotic value, which is 0. Okay, and 0 maps forward to 2 pi I, and 2 pi I maps forward to 2 pi I. Okay, so this function is post-singularly finite. Right, any questions so far? Okay, I'm going to move on. So for polynomials, we use the terminology post-critically finite instead of post-singularly finite, since there cannot be any asymptotic values. Okay, so polynomials can only have critical values. So here's the main theorem that we're going to prove today. The theorem is that given any PSF entire map, which I'll call F, there exists a sequence of PCF polynomials, which I'll call Fn, such that firstly, Fn converge to F locally uniformly on the plane, and secondly, if you restrict the dynamics of F to the post-singular set, then that is conjugate to the dynamics of Fn on their own post-singular sets for all. Okay. So you're asking for a specific type of approximation of some entire function where you want a specific type of action on some finite set. Okay. All right. So why is this sort of thing? We'll see later on why this sort of result is important in like a broader context. But in order to do that, I need to introduce some extra things from complex dynamics. So let's first take a look at why we should care about PSF maps at all. Okay, but maybe let's look at this example first. So we have f of z equal to 2 pi I e to the z. This is the example we saw before. Now, if I take fn of z to be these polynomials, so these have the form some constant lambda n times 1 plus z over n raised to n. So these are degree n polynomials, and you can check that they have a unique singular value, which is 0. And lambda n's have the value given here. Then you can see that the post-singular set, the dynamics on the post-singular set looks like this graph. So basically, you have the vertex 0. I'm not sure if you can see my mouse pointer. I'm pointing to.
No, we can see it.
Okay, great. So yeah, this vertex in this graph is supposed to represent a singular value, which is 0 for all these functions, and 0 maps forward to some point, and that point is fixed. So that is the dynamics of the post-singular set. Okay, and you can also check that Fn actually converges to F as you require. Okay. Okay. So why should we care about post-singular post-singularly finite functions? So for one thing, they're really important in complex dynamics. They've been really useful in studying the structure of parameter spaces. So here's one very well-known example. So this picture is the Mandelbrot set. What is it? So you look at all the polynomials of the form z squared plus c, and you let so what you're looking at is the c plane, and you color those c for which the orbit of 0 is bounded. Okay, so that is the Mandelbrot set, and the points that are marked by star in this picture correspond to PSF polynomials, and the graphs in these small squares for each of these points represents the dynamics on the post-singular set. So for example, this point, this star right here is c equals -1. And if you look at z square minus 1, you see that -1 is the singular value, and it goes to 0, which goes to -1. So you have a 2 cycle on that's the dynamics of the post-singular set. Now, so the point is that if you map out all the post-singularly finite functions in the Mandelbrot set, so for one thing, these type of functions are dense on the boundary. Okay, so that's one example of how they're important in figuring out the structure of the Mandelbrot set. And there have been several other, and there's several other properties that you can study for the Mandelbrot set just based on where the PSF functions are located, their dynamics, and there's a combinatorial structure that follows, and so on. Okay, so this is just one simple example, and this sort of analysis has been done for a lot of spaces of functions, entire functions, and rational maps, in fact. Are there any questions? Okay, I'm going to move on. So here's another way they can be important. Instead of looking at parameter spaces, you can look at the dynamical plane of any function. So for any function, any entire function f, the Fatou set, which I'm denoting as f sub f, is defined as the set of points on the plane such that the family of functions f iterated n times as n goes to infinity is normal in some neighborhood of z. So this is the set of normality. The Julia set is the complement of the Fatou set, and since I'm restricting all maps to the plane, I'm taking the complement on the plane. And the escaping set is the collection of points which escape to infinity under iteration. Okay. So these are all sets that are invariant under the function, and we care about them. We care about their topology, their geometry, etc. when we study complex dynamics. Let me just make one more definition. So a point z is said to be periodic if fn of z equal to z for some n, and the minimal such n is called the period of z. Now, I will call a point super attracting if this derivative here, the composite derivative of f to the n is 0 at that point. So for example, the only way you can get a super attracting point or a super attracting cycle is if you have a critical point that's periodic, so that this derivative will vanish there. Okay. So let's say z is super attracting for f. The basin of z is defined as the set of points that are attracted to the cycle containing z under iteration. Okay, I'm not going to go too much into this definition, but I'm just going to give you an example. So if you have f of z equals z to the 4, you see, for example, that z equal to 0 is fixed. And if you calculate this derivative, which is called a multiplier at z, then it is 0. And so z equal to 0 is a super attracting fixed point. And if you actually compute its basin, so that's basically that all the points that are attracted to 0 under iteration. And for this function, that basin is the unit disk. Are there any questions, or should I move on? Okay, I'm going to move on. So why? Okay, so these are just some basic things that we care about a lot in complex dynamics. So the Fatou set, the Julia set, the escaping set, and there's also the behavior of periodic cycles and so on. And these things interact with each other. So the kind of periodic cycles that you have often affect the structure of the Fatou set, Julia set, etc. So if you have a PSF function in specific, these have really nice geometric properties. So if you have a PSF function that's transcendental, so it doesn't extend holomorphically over infinity, then the Fatou set is the union of all the super attracting basins. The Julia set is the closure of the escaping set. Okay. So you have this nice breakdown of what these dynamically important objects are if you have a PSF map. So for example, if you take a function of the form lambda e to the z, you don't have any critical points, so you cannot have any super attracting cycles. So if you don't have any super attracting cycles, you don't have any super attracting basins. So you don't have a Fatou set. So the Julia set has to be everything. If you have a polynomial, on the other hand, that's PCF, then the Fatou set is the union of the escaping set and all the super attracting basins. And the Julia set is the boundary of the escaping set. Okay. So for this function, z square minus 2, the Julia set is this interval, and the escaping set is everything else. So these are some of the ways in which PSF functions are nice and useful. But the problem with PSF functions, it's hard to come up with them. So for example, if you ask me a question, what is an entire map F with infinite, a transcendental entire map with 100 singular values such that each of them are fixed? There is no way to answer such a question. I mean, even if you ask me what is a degree 100 polynomial with 5 singular values such that each of them are fixed, you would potentially be able to do some algebra with them, use a fundamental theorem of algebra or some like basic algebraic geometry or something like that and try to solve this problem. But there is no guaranteed answer. So this is the issue with using PSF maps. It's just pretty difficult to find them, and in infinite degree there is no like set algorithm to do this. One of the ways to do it is to work with topological models for PSF maps instead of holomorphic models, and then try to convert these topological models and somehow into holomorphic models. Okay. So this is what we will look into later, and we will see how this theory helps us answer the approximation question that is the content of our main result. Okay. So let's also just define what I mean by a dynamical approximation. Roughly speaking, if you have an entire function f, the sequence of entire functions fn, for the purpose of this talk, I will say that fn converges to f dynamically if, first of all, there is locally uniform convergence on the plane, and so fn converges to f locally uniformly, and there is a certain dynamical property x of f, which all the fn's also satisfy. So you want convergence in some dynamical sense. That's just what I mean by converging dynamically. Okay. In practice, if we can find fn's that are simpler in complexity than f, so for example, if fn's are polynomials, we can study the property x on the fn's instead of f, and then use that to study the property x on f. So the whole idea is to study the dynamics of f, but by using simpler approximations of f that satisfy that same dynamical property. Okay, so this is the utility of dynamical approximations. And what type of property can you care about? It can really be anything. So for example, you can ask f to be hyperbolic. What hyperbolic means is that every singular value is attracted to some cycle and iteration. So if f is hyperbolic, can we find polynomials that are hyperbolic that converge to f locally uniformly? You can ask the same thing for PSF functions. So if f is PSF, can we find PCF polynomials fn that converge to f locally uniformly, and so on. You can frame any number of questions. So here is one example of a dynamical approximation. Consider this exponential function 1 over e times e to the z. Z equal to 1 is a fixed point of this function, and it has multiplier 1. So by multiplier, here I just mean the derivative. Okay, so at z equal to 1, f has derivative 1. So if you look at these polynomials fn with these coefficients out in front, we notice that z equals 1 over 1 minus 1 over n is again a fixed point of fn, and it also has multiplier 1. And you see that, so these points go to z equal to 1 as n goes to infinity, and the functions themselves go to f as n goes to infinity. Okay, so this is a dynamical approximation. Any questions so far? Okay. So what are some examples of the type of results that that we're thinking about here? So Devaney, Lyubich, Schleicher, and a lot of others, they generally have studied entire functions and transcendental functions as limits of rational functions. And the way that they do that is they try to generalize the techniques that we use in rational dynamics to transcendental dynamics. So this is not, I mean, I'm not talking about like any type of dynamical approximation result in specific, but this is a certain point of view that's used to study transcendental functions. Kisaka has this beautiful result from 95, which states, so if you have a sequence of entire maps, converge fn converging to f, which are all, I mean, this is a sequence of entire maps, and furthermore, you know that the Fatou set of f is the union of super attracting bases. So the Fatou set of f already has this nice structure. Then what Kisaka proved is that the Julia sets of the fn converge to the Julia set of f in the Hausdorff metric. So this is an example where you don't have any PSF property or anything like that, but the Fatou set already has this structure, and then you're making a statement about the convergence of Julia sets. There's this really nice paper from the 2000s by these 6 people, where they studied a certain subset of exponential functions, and they looked at the same family of polynomials that we've been looking at before. So something of the form lambda times 1 plus z over n to the n, and they showed convergence of some dynamical property. Lastly, Helena has a result on spaces of entire functions, where she studies subsets of these spaces called hyperbolic components. And she looks at converging sequences of the form fn to f, and she shows something about how hyperbolic components in the space of the fn converge to hyperbolic components in the space of f. Okay. I have another result apart from the one stated here that talks particularly about exponential functions. So it's the first statement is the same, basically that if you have an exponential function of the form lambda e to the z, there exist a PCF polynomials of this form, which basically look like lambda n times 1 plus z over n to the n, that firstly converge to f locally uniformly, and secondly fn restricted to pfn is conjugate to f restricted to pf. But you can say further in this case. You can also figure out just by using the formula for lambda and the combinatorics of f, where these polynomials are going to live in the space of degree n polynomials. So for example, if you look at, if you fix any particular n and you look at this space of polynomials, so z maps to mu times 1 plus z over n to the n, then these specific fn's, so in the space of polynomials, you have these things called parameter arrays, which give some sort of location for PSF maps within that space of polynomials. I don't want to go into too much detail on this, but what you have is basically an angle which tells you exactly where, and an arc corresponding to this angle, which tells you exactly where every PSF parameter lives in the space of polynomials. And what you can show is, if you have a map F and you can produce a sequence of maps Fn that have specific coordinates in these parameter spaces, and you can actually write down a formula for these coordinates, which looks something like this. Okay, we'll see an example of what I mean here later, but for now, I'm just going to leave this here. Any questions? Okay, I'm going to move on. So earlier, so from this point on, we're going to talk about how to go about proving the theorem. So I said that we're going to use the fact that we cannot work directly with PSF entire maps because it's not quite clear like how to even write down formulas for them or how to find them. So we're going to work with topological maps from now on. So what is the structure for a topological map that you need in order to like make it as close to entire as possible? So here's the basic thing. So if you have a branch cover that has finite degree, we'll call it a topological polynomial. We'll call a branch cover topologically entire. I'm sorry, is there a question? Okay, we'll call a branch cover topologically entire if locally it looks like a holomorphic map. So you have, for every x in R2, you have a neighborhood of x and a neighborhood of this image and coordinates on these neighborhoods where the map looks like z to the d for some d. And lastly, so the crucial thing is, so let's say you have a topologically entire branch covering. So if you give me any complex structure, basically a quadratic differential on R2, such that with this complex structure A, R2 comma A, that Riemann surface is equivalent to the plane, then this Riemann surface R2 comma F star A, where F star A is the pullback of A, can be equivalent to either C or A, because the only restriction you have on it is that it's simply connected and it's not the sphere. So you can have either C or, sorry, I meant to write either C or D. So it can be either the plane or the unit disk. So if X is the plane for every complex structure A, then F is said to have stable parabolic type. If F is the unit disk for every complex structure A, then we say that F has stable hyperbolic type. Okay. Now the point is, for a general topologically entire branch covering, you don't need to have either. It is not necessary that F has either stable parabolic or stable hyperbolic type. So you can have, for one complex structure, you can get the plane. For another complex structure, you can get the disk, and so on. But if you put further restrictions on F, you see that nice things happen. So let F be a topologically entire branch covering. If the set of singular values is finite, then F has stable parabolic or stable hyperbolic type. Okay. So lastly, I'll just make one more definition. So that the topological equivalent for a PSF entire map that we're looking for is something that we'll call a Thurston map. What is it? So an entire Thurston map is a topologically entire branch cover where firstly, PF is finite. So the map is postsingularly finite. And secondly, F has stable parabolic type. Okay, so when you pull back flat structures, you should always get flat structures under F. That's basically what I mean. Okay, so if F satisfies these properties, it's called an entire Thurston map, and we'll use this notation to denote such a map. We'll see in a bit why this stable parabolic type restriction is important.
So Mala, sorry to interrupt. Can you say a few words about the proof of lemma 9? So how do you prove this?
Yeah, that's a good question. So you basically, right, I think you, okay, I think the first thing you can show is that if you have isotopic maps and one of them pulls back to like a thing of one type and the other one pulls, then the other one also has to pull back to a thing of the other type. And then I think okay, so if you have finite type maps, then there's like a nice breakdown of the domain into like these like nice looking fundamental domains. And you use that somehow to like look at what the pullback looks like on each of these domains and show that they had to pin together nicely. So it goes something like that. Yeah. I think there's a proof. I can give you a reference at the end of the talk. Okay, yeah.
Okay, thanks.
Mm-hmm. So, okay, by the way, this problem is called a type problem to figure out for any given map F and a complex structure A, whether this F is X is C or the unit disk. It's a pretty difficult problem in general. Okay, so there is no comprehensive solution to this.
Well, this is why I asked the question, right? I mean, the type problem is known to be a very delicate problem. So I'm a bit surprised by your lemma 9.
Yeah, but yeah, this is I'm sure I can give you a reference, but yeah. Okay. So yeah, so if you have two topologically entire functions, f and g, we just need one more thing. So if you have a topological map, since we're talking about like lifting complex structures and stuff like that, often you don't need to care about isotoping the map. So I'll give like a definition of this that is going to take care of things like that. So if you have two topologically entire pairs of maps, or basically two Thurston maps, f and g, they are said to be Thurston equivalent if there exist orientation preserving homeomorphisms, phi0 and phi1, which, okay, firstly, you need them to be isotopic relative to PF, and you also need this diagram to commit. Okay, so it's some kind of topological equivalence, not equivalence quite, but like an almost equivalence. Okay, so additionally we say that F is realized if there exists an actual holomorphic entire function that is Thurston equivalent. Okay, and we say that F is abstracted if it is not realized. So generally, figuring out whether an entire Thurston map is abstracted or not is a pretty difficult problem. Already, it's not been solved, but it has been solved for topological polynomials. So if you have a finite degree Thurston map, it is abstracted if and only if it has a topological abstraction called a Levy cycle. So what a Levy cycle is basically some multicurve on the plane, or in this case, the sphere, and it has certain nice properties under iteration of F. So you can this problem of whether F is equivalent to something holomorphic, somewhat surprisingly, is just dependent on a topological condition. So this has also been extended to several special families of entire functions, such as the exponentials. And it is also being studied for the structurally finite family, but I don't think that paper has been published yet, so I've not cited it here. Okay, but it is Sergei Shemyakov's PhD thesis, and yeah. Okay, it is not known whether this is true for all entire Thurston maps. So beyond whatever I've stated here, I think there are some results for rational Thurston maps. I know, Mario, you have worked on some of this, Misha and Anina, and yeah. I know some other people have done some work, but there's no like, I mean, in the rational world, we know what type of abstractions we can have. I mean, we know what an abstraction looks like as a multicurve, but we don't like have a classification of Thurston abstractions. And in the transitional world, we have absolutely nothing. But for exponential functions, we know for a fact that every abstraction is a Levy cycle. And for the structurally finite family, I think it is conjectured that it is a Levy cycle. So yeah, and all the Thurston maps that we produce in this theorem are going, I mean, in this talk are going to be Thurston maps that are always realized, because we are looking for a holomorphic result. But okay, let me go on. So how do we, okay, so far I've been talking about holomorphic PSF maps and topological Thurston maps. Now, how do we go from one to the other? How do you start with, I mean, if you know that a map is realized, how do you realize it? So one way to do this is to iterate this like operator on this big space, which is what I'm going to describe in this page. So the diagonal space R to A, or equivalently S to A union infinity, is the diagonal space of the sphere modeled with A union infinity. Basically, you look at all homeomorphisms that are orientation preserving on the sphere, and which also map infinity to infinity, modulo some nice equivalence relation, which says that two such maps are equivalent if there is some affine transformation M such that M composed with phi is equivalent to psi, is isotopic to psi relative to A. This is a very technical definition, but this space is like pretty well known. So if you look at like any textbook on mapping class groups, for example, I'm sure you can find this. So the point is, the reason that we needed stable parabolic type, and the reason that we needed the definition of the Thurston map that we took, is so that the following works. So if you give me any element in the diagonal space, which I'll call phi, then there exists an element psi such that h equal to phi composed with f composed with psi inverse is entire. Or in other words, this diagram commutes. So you always know the left arrow, which is f. The bottom arrow is some element in diagonal space, phi. The point is there exists a top arrow so that the completion of this diagram is an entire function. Okay. And in order for this to always work, you need f to be of stable parabolic type. So we'll also additionally define an operator on this diagonal space, which is called the Thurston pullback operator, which takes every phi, which is the bottom arrow, to the element containing the top arrow. So it sends phi to psi. And this is a holomorphic operator on this diagonal space.
Can I ask another question? I mean, you just mentioned the holomorphicity of the operator. Do you have a reference for this?
Yeah, I should probably have noted this down here, but yeah. So one reference is, for example, so they prove this for exponentials. One reference is Hubbard, Schleicher, Shishikura. There is a paper where they prove that obstructions for exponentials are Levy cycles. They prove the holomorphicities of this map here. And I think their work holds in generality for all entire functions. Yeah. So yeah, I'll put the definition here again. So the point is, this point sigma f has a fixed point in diagonal space if and only if f is realized. Okay, so that's what we need this operator for. It tells you whether f is realized, and iterating it and finding it a fixed point also helps you find a realization for it. And you also know that sigma f is weakly contracting in the diagonal metric. So if you have a fixed point for f, it has to be unique. Okay. I'm not going to define the diagonal metric exactly. The point is there are various metrics on this diagonal space. One of them is the diagonal metric, which is complete. There is another one called the Weil-Peterson metric, which is not complete, but the completion is a compact ball. There's third thing called the Thurston metric, and so on. But yeah, so this operator in the diagonal metric is weakly contracting. Okay. Okay, now we have introduced all these things. So let's look at the strategy for proving the main theorem. I haven't written down a lot of things, but I can tell you what's going on. So, okay, we are going to translate. Let's recall what theorem A is. Theorem A is basically that if you have a holomorphic PSF entire function f, there exists a sequence of holomorphic polynomials which are PCF and converge to f, and you have the correct dynamics on the post-singular set. Now we are going to translate that into a problem, into an approximation problem in diagonal space. So basically, I'm going to show, firstly, there is this other main theorem that if you have a Thurston map F, an entire Thurston map, and a sequence of other Thurston maps Fn, so if Fn converge to F in a combinatorial sense, which I will define in a moment, then the sigma Fn's, the Thurston pullback operators corresponding to the Fn's, converge to sigma f locally uniformly on diagonal space. Okay, so this is an approximation of these operators on diagonal space. And these are all functions with the same post-singular set. So all these operators act on the same diagonal space at Dec6th2023. Okay. So what do I mean by combinatorial convergence? So here is one thing that I mean. Roughly speaking, what it means is that all the fn's eventually lift all closed curves in this space R2 minus A the same way that f does. So what exactly does that mean? So this means that there exist points T, B, and B, so that fn map the Bn to T and f maps B to T, such that, so if you take any loop in the codomain that is based at T and doesn't pass through A, if you lift it under F, then that is closed if and only if when you lift it under Fn, that is closed eventually for n large enough. So basically, what I mean is, so if you have all these like points B and B, so that if you take any curve in the codomain, if you base at T, if you take the lift of the curve under F and base it at B, then that is going to be closed if and only if eventually when you lift it under Fn and base it at B, and that's also closed. Okay, this is hard to describe without an image, and I'll show you an image in a minute. And the second condition that you need is, so these lifts actually need to be homotopy. Okay, so if for each end there exists, if the curve is closed, then for each end there exists paths, so that when you take a curve in the codomain, when you lift it under F and when you lift it under Fn, these paths conjugate one of the lifts to the other. Okay, so before I go to the strategy, let's look at an example. So, okay, here is one way that you can describe a Thurston map. So the top picture is the codomain, the bottom picture is the domain. This is the Thurston map here. So it has the following formula: root of ln2 times 1 minus x z square. For ln2, I just take the argument in 0 to pi. So the top graph is, so the points A1, A2, A3 represent the post-singular set in this case. So 0 is, I think, in fact, a critical value, and one of the others is an asymptotic value, and one of the asymptotic values maps to the other, and that one is fixed. So you have some nice dynamics here. So this is the entire post-singular set. And the top is a graph which is based at some point T, which I should have mentioned here. So the center point is the point that I'm calling T. And you have this graph has a petal going through each post-singular set. Now the point is, so if you just restrict f to this graph, and if you know what f restricted to the graph looks like, then it is possible to just recover f from this. Okay, so in order to recover f, you just need to understand what happens on this graph. So when you take the pre-image of this graph under F, for example, you get this big graph where, again, so since the post-singular set is invariant, it's forward invariant, you still have the same like A1, A2, A3 points. The other pre-images are inside these like small petals, but I'm not marking them. Now this unbounded face tells you that A3 is an asymptotic value. So this big red unbounded face maps to the small red petal, maps into the bounded region, and you have two unbounded regions that map into A3. So it's an asymptotic value twice over. Now, if you know what the map F is restricted to the bottom graph and mapping to the top graph, then you can recover it. Okay, so this is one other way to like think of Thurston maps. You can just think of them as maps from graphs to the graphs. So one way to recover F is, so if you know the map on this graph, you can just you can remove this graph from the plane, and on each connected component of the complement, you can extend F in some way. So that's one way to recover F up to isotopy. You can't recover the exact formula, of course, but you can recover like all the properties that you care about. So when I say a combinatorial approximation, what I really mean is, so you look at the bottom graph, okay? If you look at this sequence of graphs, what I'm really doing here is I'm looking at B, and I'm taking n balls in B in this graph, and I'm just like looking at that like subgraph, and I'm finding a way to close up this subgraph in some way, okay? And I'm describing a Thurston map based on sending each of these subgraphs into this top graph here. Does that make sense? I don't know if I'm like describing this in a special in any like legible way. So let me say that again. So I have this big unbounded graph at the bottom. Okay, I find a sequence of graph that somehow approximate that big graph that satisfy all these like loop properties that I want. And from these sequence of graphs, I define a polynomial Thurston map on the whole plane just by defining map on the graph. And once I do that, I have what I want to be a combinatorial approximation. Okay, so the combinatorial convergence condition just tells you what the degrees of these restricted to like each of these loops can be and so on. Okay, so what is the strategy for proving main theorem A? The first step is what I just said. You construct a topological polynomial Thurston maps, which are called Fn tilde, that converge combinatorially to F. So firstly, you construct a sequence that has combinatorial convergence. One way to do this is to somehow find a way to like restrict these graphs to subgraphs, this big graph to subgraphs. And they also need to have the property that F restricted to A is conjugate to Fn restricted to A for all n. So once you do that, you use main theorem B, which implies that sigma Fn converges to sigma F locally uniformly in diagonal space. So if you have combinatorial convergence, then you have this. And you also show that using the fact that F is realized, using the fact that F is an entire function, you show that all the Fn tildes are also realized as holomorphic PSF polynomials Fn. So all the sigma, since you have this locally uniform convergence of the sigma maps, if sigma F has a fixed point, then the sigma Fn's also have to have fixed points for large n. So the Fn tilde are realized as Fn. And then lastly, you show that you actually have Fn converging to F as required. Okay, let me just say a little bit about what goes into proving this main theorem B, since I've not said anything about that. So the combinatorial convergence condition is actually going to imply some sort of topological convergence, meaning that, so if you have a sequence converging combinatorially to a limit function, then I can produce some sort of isotopic sequence that actually agrees with the limit function in larger and larger sets. And we're going to use that sort of result and some combination of the lambda lemma, etc., to show that there's this geometry convergence of the sigma maps that's happening here. But I don't want to say too much about this since I think I'm running out of time and I want to show you some examples. So here is one example of convergence. So okay, so this picture is in the space of exponential functions. So all functions here of the form lambda e to the z, and I'm looking at the lambda plane. The points colored black are the lambdas for which the singular value does not escape to infinity. I've marked a specific point as star, which approximately is this value 1.16302 plus 0.71 RE. And this point is postsingularly finite. Okay. In fact, the dynamics on this is, so there is a single critical value, it jumps 4 steps and then it jumps into a 4 cycle. Okay. So it has pre-period 4 and period 4. And so I'm also going to show you what the approximating parameters look like. So each of these pictures is a space of degree n polynomials with a single critical point. So every one of these, so like lambda times 1 plus z over n to the single picture. So it's not very efficient. Even when you go to degree 200, the real parameter is not as close to what you need it to be. So I have 1.16, but here I only get to 1.15. But another thing that's curious is that the location of these things in these spaces looks more and more like the location of lambda in exponential parameter space. And another way to describe this is, okay, so this point lambda, it has something called an external address, which is a combinatorial sequence, which tells you where it is in the exponential parameter space. Now for this particular lambda, the address happens to be 0, 0, 0, minus 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, and so on. Now if I look at the corresponding location of the degree d parameter in its space, then the sequence that I get is this. So I get 0, 0, 0, d minus 1, 0, 0, 1, 0. Now you can also interpret d minus 1 as modulo d as minus 1. So you essentially just have the same sequence. So if I need to like describe all this in detail, I'd have to like go into the theory of like where these sequences come from. So I'm not going to do that. All I'll say is there is an actual topology. There is an actual like analytic convergence of these lambda d's to lambda, and there is also similarity on the post-singular set. And lastly, there is also this like combinatorial convergence of the coordinates of these points to the coordinate of lambda. So this is something that one other thing, if you know the theory more, is if you look at the Hubbard trees of all these polynomials, lambda 1, lambda 2, etc., all those Hubbard trees will be the same topologically. And if you look at the corresponding homotopy Hubbard tree of this lambda, that will also be the same as what you get for all these polynomials. So yeah. Okay, so this is like there is a bunch of senses in which this convergence is going on. So okay, let's look at some questions. So first question, since we just looked at this example, is can we approximate spaces of entire pairs of maps by spaces of polynomials? So is there some sort of, if you give me a huge space of entire maps, is there a canonical sequence of spaces of polynomials which converge in space? But I'm only just restricting to PSF maps in a big space. So that sort of thing is exactly what's going on in the exponential sense. If you mark all the PSF parameters in the space of exponential maps, then in some sense, you can show that the corresponding PSF polynomial spaces converge to this exponential space. But the point is, can you do it for general entire functions? And here I should also mention, so I said that you can construct a combinatorial approximation which are polynomials, but you can construct like infinitely many combinatorial approximations. So here I took a specific sequence of finite graphs that approximate my given infinite graph, but you can theoretically produce a different sequence that converges to my infinite graph, and you can show that that's going to correspond to a different sequence of polynomials and so on. So if you can do that sort of thing, then that's it. So that really tells you that this approximation that we're constructing is non-canonical, and it gives you a way of constructing infinitely many approximations. But if you want something that's consistent across spaces, then you need to put additional conditions on this. So this is a pretty non-trivial question. The second question is, can we use PSF approximations for constructing general approximations of like any properties? So I mentioned at the beginning of the talk that PSF maps are important in studying the parameter spaces of entire maps. So if you perturb a PSF map, for example, often very nice things happen. So can you use perturbation theory, for example, to produce approximations of hyperbolic maps or parabolic maps using PSF approximations? That is one question that I am studying. Lastly, not lastly, but can we do the same for transcendental metamorphic functions? So if you don't have the entire property, does this theory still go through? I suspect that it will, because there are not a lot of places here where we actually use that the map is entire. Everything that I stated for Thurston theory, etc., all of that can be easily generalizable. But this is something that should be checked. And lastly, this is the biggest question. So can we use polynomial approximations to study obstructions for entire maps in some way? So let me break down the problem. Say we start with an entire map F, an entire Thurston map F, so we don't necessarily know that it is realized. We can still produce topological polynomials with sigma Fn converging to sigma. That's what main theorem B says. So I just said if F is realized, then you can use this sigma convergence to show that the Fn's are realized. But then the question is, can you say the opposite? Like, it's a converse true. So if infinitely many of the sigma Fn's have fixed points, does sigma F have a fixed point? So here are two things that can happen in this situation. So if infinitely many of the sigma Fn's have fixed point, firstly, if infinitely many of those live in some bounded set in type Miller space, then yes, absolutely, the sigma Fn is going to have a fixed point because you can take a subsequence that converges and so on. But if not, if every single subsequence of the fixed points of the sigma n go to the boundary of go to infinity in type Miller space in some sense, how can we study that? So in the polynomial world, and in fact in the rational world, these operators sigma f, so they are known to be locally contracting, locally Lipschitz in the Teichmuller metric. But when you translate the problem into the Weil-Petersen metric, in fact, they are globally Lipschitz. There is some Lipschitz constant that's like a uniform contraction. And they use this. So there's this really nice paper by Nikita Selinger that uses this to show that if you take sigma f for a polynomial map or a rational map, then this extends to the Weil-Petersen metric and therefore the augmented Teichmuller space continuously. And you can always find a fixed point in the boundary of that augmented Teichmuller space. But such things do not happen here. Like I think it is conjectured that sigma f in the entire case or in the general transcendental case does not extend continuously to the augmented Teichmuller space. So you cannot use that method of finding obstructions. But you can still try and study how this divergence of the fixed points of the sigma fns is taking place. And by using that, you can try to show that obstructions of f have to have a certain form. They have to be Levy cycles, for example. Okay, so that is one thing that is a major problem, but it is a different perspective on looking at Thurston's theorem or like obstructions for entire functions. And I just wanted to mention that. Okay, so since I mentioned approximation of spaces by spaces, I just wanted to show you a clearer picture of like, what this approximation looks like for the exponentials. So each of these pictures is again a picture of the space of polynomials of degree n with a single critical point. So this is degree 4, degree 6, degree 8, and so on. And when you move into infinite degree, this is the picture that you get, and that's the space of exponential maps. Okay. So I just want to end here. Are there any questions?
Yeah, thank you. Yes, let's first thank Mala. And let me open the discussion. So any comments or questions? Well, I have a question. Your Teichmuller spaces for these PSF maps, right? They're still finite dimensional, no?
Yeah. Yeah. So they have dimension cardinality of A minus 2, I think. Yeah.
I mean, this problem that you brought up, can we get from the fixed points of these polynomials to a fixed point of the map? I mean, that's actually a very interesting problem. My current PhD student actually has found another proof of Thurston's theorem, at least in the case of 4 post-critical points. So actually, this might be a way to approach your question, at least in a special case.
Okay. Can I ask which student this is?
Zach Smith, actually.
Okay.
This is not yet published, but this is actually very interesting direction to explore. Other comments or questions? Well, let me